It's 10:31. Shall we start? Um,
Can you hear me?
yes. Yeah. Yeah. We'll.
Danusha, let me double check
Indigo,
the
can you
live
hear me?
stream and then give me one.
Yes, I can hear you.
I'm not hearing anything. Hang on.
Yes, go ahead, Danusha.
Okay. Hello,
Yes.
everyone. Welcome to today's seminar of the CUFSAA Distinguished Speaker Series, organized by the Colombo University Faculty of Science Alumni Association. Thank you for joining us from different parts of the world, mainly from North America
Can you hear me,
and Sri Lanka.
Indigo?
Yes.
I'm not hearing you guys. Can you hear me?
Yes, we can hear you.
You can, but I can't hear you guys. I don't know why. That's odd. Oh well. Should I start?
Uh,
No.
so, Danusha, please go ahead.
Yeah. So this is the 11th seminar talk in this series and the first one for this year 2026. So again, on behalf of CUFSAA, I am delighted to welcome you all for this session. To begin, we'll play a short video introducing our organization and about this seminar series.
Colombo University Faculty of Science Alumni Association, CUFSAA, proudly presents a distinguished speaker series to uplift the knowledge of aspiring students and budding scientists in the Faculty of Science at the University of Colombo and Sri Lanka as well. In this series of lectures, CUFSAA features accomplished scientists and key opinion leaders in different science streams to present the advancement in their field of expertise. This seminar series is a collaborative effort between CUFSAA and the Colombo University Faculty of Science. Welcome to the Distinguished Speaker Series of CUFSAA.
I can hear you now.
That's good. So it is my pleasure to introduce today's speaker, Professor Krishni Wijesooriya. So before we begin, a quick note on the questions. We will have a quick Q&A session 15 minutes after the talk, but you don't have to wait till the end. You can type in your questions in the Zoom chat window, and also after the talk, you can unmute yourself and ask your questions. So to briefly introduce our speaker for today, Professor Krishni Wijesooriya received her BSc Special Degree in Physics from University of Colombo in 1993 and her MSc and the PhD studies in Nuclear Physics from College of William and Mary, Virginia in 1999. She joined UVA Medical Physics program as a faculty member in 2008, where she has served since then. And she is now the chair of Medical School PNT Committee, member of the American Association of Physicists in Medicine, in global research and innovation. And she's also the founder of Rainsight LLC. So today's speaker is a clinical medical physicist at University of Virginia with extensive experience in radiation therapy program development. She has initiated and developed many clinical programs at UVA, including IMRT, total body irradiation, and motion management techniques. She has significant expertise in linear commissioning, and she is the primary physicist in national clinical program trial protocols at UVA. Her research focuses on modeling immune suppression following radiation therapy, AI-driven treatment planning, and improving patient safety through advanced QA methods. She is also the principal investigator of an NCI-funded clinical trial at the UVA Cancer Center. She has authored over 30 peer-reviewed publications and book chapters and actively mentors undergraduate and PhD students. And with that, I am pleased to invite Professor Krishni Wijesooriya to begin the talk. The floor is yours.
Thank you, Dishant. And thank you, Sajid, for the invitation. Let me pull up my talk. Share my screen. I'm going to share my whole screen because I'm having issues with my video. So hang on. I share the whole screen. That way I can go back and forth. Individually, I can open them. So let me go to the beginning of my talk. This one out of the way. Right. Go to the PowerPoint mode. You guys can see the presenter mode, right?
Yes, we can see it full screen, yeah.
Yeah. All right. So it's a pleasure to give this talk, especially for University of Colombo crowd, because I came from there, and throughout my talk I have these beautiful pictures very dear to my heart. Of course, about Sri Lanka. Whenever I go give talks, I have a bunch of them in my slides. So I gave the title From Bedside to Model in a Multi-Test Analysis of Immune Suppression. Can you guys hear me well? Can you hear me well?
Yes.
Yes,
Good.
we can hear.
Good. Let me know. Otherwise, the whole point is information transfer. So, but I also would like to spend a little bit more time before I get into just this particular research on medical physics careers, how I got into this field, and what kind of opportunities are out there for medical physics in the United States, at least. Okay. So these are my conflicts of interest. So this is the abstract I gave Sajid. So this is really, really important because next generation of physics and engineers will be able to run clinical trials. Currently, in the world, there's only about 5% of physicists who have run clinical trials. So I think it's about to change because of AI and modeling, because we are the ones who model, we are the ones who knows how to validate things. So I have two outlines. The first part is about medical physics. So this part I would share my thoughts on my career as well as different branches of medical physics, essential tools that we use on a daily basis, and going into the future directions, and then how to become a medical physicist. So my field, I got my PhD in nuclear physics from Jefferson Lab, and my thesis experiment was basically using a high-energy electron beam to heat a radiator and create infrared photons, and I used that to heat neutron and proton targets. And by doing so, I was trying to probe the nuclear effects, electromagnetic form factors, and things like that. So during this time, I did not know there was a medical field called medical physics. So these are some of my nuclear physics publications using Benflon photons. And then one day I saw a Physics Today article cover page, a proton therapy machine. So I read about it and I thought, oh my God, we can do this as well. So I did a career change, and these are some of the things I've done since then in the field of medical physics using exactly the same tools. So if I were to go back a little bit here in my original life, I was using deuterium proton tablets. Now I use the same system, but I have very precious targets. So I had to be very, very careful, accurately, precisely targeting the tumor. So currently I am a board certified academic medical physicist, work at University of Virginia. I have multiple different hats. So I provide clinical medical service to radiation oncology, work on research projects and write grants, educate the next generation from undergraduates to graduate students to medical physics residents who already have PhDs and medical residents who already have MDs. So what do we do? Medical physics. So we, with a profession with education specialized training in concepts, techniques, and applied physics in medicine. It could be a broad range of techniques and tools, starting from imaging to how interact with radiation interact with matter, to depth of curves, to even IT. So there are 4 branches of medical physics: therapeutic, diagnostic, nuclear, and medical health. Most of the medical physics are in therapeutic medical physics because you cannot treat without the signature for medical physics. So to show a little bit about how this field came about. So Wilhelm Röntgen, we all know, who got the Nobel Prize in 1901 for discovering X-rays, right? And then Marie Curie came up with the spontaneous radiation, who ended up getting 2 Nobel Prizes for her work. And even today, International Day of Medical Physics is devoted to her birthday. So some of the tools that we use in medical physics on a daily basis are actually very simple things that ended up being bread and butter of medicine. So, for example, CAT scan, CT scan, it is nothing much. Basically, you have a KV photon source and it goes to the patient's body while rotating around, and you have a set of exit detectors that you detect its transmitted photons, and simply by rotating this force and acquiring data around the patient, we can have a bunch of different differential equations that you can solve to get attenuation factor for every one of these small little cubes if you were to divide this city. So they got the Nobel Prize for that. This is kind of a really, really necessary part of radiation therapy for 2 reasons. One is actually you get the image, so you can delineate the tumor as well as the organs at risk. So remember, these are taken, the CT images are taken at kilovoltage energy. So the photoelectric is the dominant component. So, but when you obtain this attenuation coefficient for each one of these boxes as shown here, you can actually traverse the megavoltage energy that we use to treat the patient and traverse through the photon beam and calculate the attenuation and create the dose distributions accurately for a given patient's tumor, and also not just the tumor, the organ matrix, more importantly. So we also use positron emission tomography on a daily basis, which basically you have the FDG tracer, PET imaging. So basically it's metabolism of the tumor, highly active tumors absorb more. So, and then these 18 fluoride is really active, so it basically emits the positron. That emits positron interacts with the electron very quickly and then create a photon pair opposite each other. That's how we detect these using single detectors and create a PET image. So these are daily things that we use for pre-treatment tumor localization, or even to post-treatment or mid-treatment to evaluate the efficacy of the treatment. Then comes the MRI, so you know NMR, and then we use the NMR, basically the proton spin that basically aligns to a given magnetic field, and then you basically, different organs in our body have different levels of this alignment. So that's how we create this imaging technique called MRI, which is actually really, really good for soft tissue contrast. So you can see in the left-hand side here, you have MRI for an abdomen, a liver case, and a brain tumor. can clearly see the tumor, and the CAT scan on the right-hand side. Really, very, very, very hard to determine where the tumor is. So this is also bread and butter of our field. So we use these imaging modalities on a daily basis for patients. So briefly about radiation oncology. So we use high energy beams, 6 to 15 MV, not that high as the Jefferson lab gives in the GeV regime. So this is enough to kill cells, can easily penetrate deep into the human body. For example, 6 MV beam you can create plants for anywhere in your body. You actually very rarely need to actually use a 15x. So they are highly collimated, intensely high fluence beams, ideal to kill cancers, but the challenge is to kill the cancer while sparing the healthy tissue. So here's the depth dose distribution. So you can see x-axis the depth in centimeters and relative dose for a 6 MV beam. There are two here. One is actually the softer beam, which is the pink one with the flattening filter free mode. Where it has a low energy component. So, but we can see maximum dose is about 1.5 centimeters, but you can 10 centimeter depth is like 66.7, but you could use this beam to treat anywhere in your body. So similarly, we have protons. So at UV, we don't have protons, but proton is a technique that people use. It's basically we have the proton beam going through the patient's body and then reduce energy, but suddenly it deposits all of its energy while struggling at one given point. Nice thing is there's very little exit dose. So, but if you have to treat a tumor that has some depth, you can use multiple different energies shifted so to cover that whole area. So here, Varian Medical Systems is one of the leading providers of medical linear accelerators. More than 50% of the share is from this company. So it's these two Stanford brothers who came up with the idea of klystron that started their company, and you can see here an inside view of a LINAC. So you have an electron gun, waveguide, you have a 270-degree bend, and then you have a bunch of collimators and the flattening filter here. So this is the treatment head. And you can see the MLCs of a treatment machine. So they are really, really thin. So, and also middle safety is like 0.5 centimeter, and then the out one is like 1 centimeter large. So you can see the procedure resolution are really, really good. So I don't think this is gonna work, but let's see. I wanted to show you this. If it doesn't work, I'm gonna for a minute and go to my folder and open something. Bear with me. So this is the Rapid R. So you can see a treatment here that in 1 minute you can treat a patient's tumor. So this goes around the patient. Patient is lying down here. We are treating the brain here. MLCs are modulating constantly, and depending on where the MLCs are, it gives a modulated fluence, and you can create these things. So you can spare the healthy tissue and give the tumoricidal dose to the tumor. So I'm going to stop this thing and then go back to my talk. All right. So this is a plan, a standard plan for a lung tumor. You can see actual view of the lung tumor is here, and you have the aorta and all the critical structures, spinal cord, and so on and so forth for a given patient. You can see this is kind of what we normally use, the dose distributions, basically the energy deposited per unit mass. X-axis is the dose and Y-axis is the normalized volume, because you can put all the different volumes from lungs that are 2000 cc's versus like something that is 10 cc's on the same page. So we can look at the clinical goal to see whether it's a decent plan that we can proceed. So one second. So this is another machine, tomotherapy. So you can see here, this was developed by a medical physicist from Wisconsin. So it treats slice by slice, and it has a binary collimator here. And you can see head and neck treatments, and there's a lot of critical structures in head and neck treatment. So it's a mostly involved organ risk in this scenario. So I want to touch a little bit about other techniques. So for example, we can evaluate the motion of a tumor. It's not going to work, but so some tumors in our thorax and abdomen can move up to 3 centimeters. So long time ago when we treated, the tumor is not where we wanted it to be, so we are missing the tumor. So nowadays we use 4D CT that takes into account the motion with respect to time and create an internal target volume, and we can treat. And newer technologies available are you can track the tumor in real time in this case. To talk to you a little about the future of radiation therapy, it's a really interdisciplinary field, and more nowadays because of AI. For example, you can use nanoparticles to transport through the body and use it to sensitize the tumor, radiosensitize the tumor, so you can get a higher therapeutic ratio for the tumor for the same treatment plan. So there are multiple different imaging modalities now available: tumor resistance, for example, oxygenation, cell proliferation. These are all different techniques of PET imaging that we can use even today. So we can use genetic markers to guide the treatment, model the tumor microenvironment, and also use other new technologies like radiomic features that characterize the tumor and treatment efficacy. I will touch base on multiple different things in the following slides. And even today, we have the ability to do treatment plans that I showed you earlier automatically. So it will take like less than a minute to give you a plan, which took normally about a day for dosimetries. So here's a slide on machine learning based radiomic features. Radiomic features is something that accesses the texture features of an image. Right now, across the world, there's so much data available that they are not used. Only 1% of that data is really used, because physicians look at the tumor and say, is this a tumor? What is the stage? And so on and so forth. But that image is never used in a voxel by voxel basis. But we have tools right now developed by multiple researchers that we can access not just the image intensity, but the texture features, basically looking at intercorrelations of these different voxels and coming up with patterns that you can use. For example, tumor might have a different pattern compared to the rest of the liver. So you can use that kind of features to come up with predictive models. So currently, this is a process that we have in radiation therapy at least. So every step of the way, we have AI-based radiotherapy workflows, and it is changing every single day. So for example, treatment decision-making, imaging and simulation, treatment planning, even plan approval, radiotherapy delivery, follow-up care. These are all AI-driven, and it will be even more in the future. So that's why the young generation has a lot to do. This is going to be a very rich field in the following decade because of AI evolution and so much, and also the data that we have in this field. So, for example, let's take a look at modeling the tumor microenvironment. I'm very interested in this field, by the way. So, for example, you can go from outside, like the biomarkers that you have from the blood, that the immune system, and then you can take different omics data. For radiomics, I already talked about, proteomics, genomics, and all of these omics data are available for these patients, and you can input that, and you can create mathematical models and network structures that create predictive models. So we can basically model a hybrid twin of the tumor microenvironment for a given patient. So now I'm going to spend a little bit more time. I think I have about maybe 25 minutes. So machine learning to predict radiation-induced immune suppression. So this is a subject that I work for 7, 8 years now. So there is a theory that when we kill the radiation, we use the radiation to kill the tumor. Up until recent, for the last 100 years, what we have done is use the radiation as a sledgehammer, basically to break the DNA double strand, right? So you kill the tumor. But there's a lot more we could do from radiation called the soft kill. So it's basically what could happen. This is a theoretical model, and it's also sometimes people have seen evidence of this in the mouse models. So if you target the tumor with radiation, it will break these little tumor pieces, and they're called immunological cell death. These little tumor pieces could be taken by these immune cells, dendritic cells, for example, and go back to the blood circulation and go to the lymph node. And in there, it will find its match. See, each one of these immune cells, we call them lymphocytes or T cells, they will have a receptor for themselves. So this receptor could identify, if they could identify this particular tumor piece that's brought by this dendritic cell, they will create two bonds, and that two bonds would create an army of the same type of T cells. Those are cytotoxic. That means they can kill the tumor. So they could get released back in the bloodstream, go all over our body, and basically kill any tumor cells that's left over from after the primary radiation treatment. So this is a very powerful thing. You can use it as a vaccine. So every single patient has a slightly different tumor component, DNA. So you cannot make a medicine or something for each one of those patients like the immunotherapists do it, right? But if you could create your own body to create a vaccine, that patient's whole body, anywhere in the body, if you have tumor cells, they will get killed by it. So it's a very powerful thing if we could optimize this scenario for every single patient. So, and secondary outline of my talk, which is what I was going to do originally. So I'm going to talk to you about lymphopenia, which is the lymphocyte kill, which are the immune cells in our body. I ran a clinical trial as a PI. You can find that information in the clinicaltrials.gov. So we have created a predictive model for this, and I'll talk a little bit about those. And then this generalized model could be applied to, already we are applying it to advanced stage lung cancer and the pancreatic cancer right now. So briefly, this has been, I don't know if you can see the bottom of it, unfortunately not. So this theoretical framework has been there since 2013. It's more than a decade ago. So what happens is in our body, you have these tumor cells that get broken up and carried away in the lymph nodes, as I said before, get expanded, and it goes to bloodstream and it starts killing the tumor. So there are inhibitory mechanisms as well as stimulatory mechanisms, so that we have to pick and choose to optimize the scenario. So in our body, all of us, tumors are occurring all the time, but our immune system is so strong, it will kill those tumors before we even notice. So that is what we could do with the immune system, and immunotherapy is trying to target those immune cells in our body. So there are, unfortunately for us, there's another process going on at the same time. One, of course, is the one that I explained, in modulated immune system. Other thing is that radiation can kill these immune cells a lot, because these immune cells are really, really radiation sensitive. So you can see we are interested in these T cells here. So 70% of our body's immune lymphocytes are actually T cells. So what we want to do is to spare the immune system from radiation, and also at the same time create an environment that we can create a vaccine-like effect. So I'm telling you a lot of biology, even though I used to be a nuclear physicist. But that's not the point. So modeling part is the most important, because you all are the next generation listening in here could do similar things, and sky is the limit. So so it's been shown by many others. The immune system lowering the immune levels in the body could lead to lower survival even after treatment, and also hospitalizations, and lots of negative things for multitude of tumors. So we also did some work along the same lines. So we saw that survival of these patients are significantly lower when you have lower immune cells in your body. So not only that, these T cells functionality, even in the same number, would be lower when you have them affected by radiation therapy. So now I have a video to show, but I have to show this. So I'm going to go back. Here. Here is my thing. I think this is the one. So you can see, this is what happens inside our body. So try again. Immune cells are highly mobile. They go through your blood circulation, it goes to your lymphatic circulation, and it goes through all the organs in our body, and it circulates all the time at different rates. So for example, I know why it is not working. So for example, blood circulation, every 60 seconds it moves back and forth, right? So not liking this.
Maybe you can reopen it.
There we go. So you can see the radiation beam is coming. It's very localized. I'm only showing a part of the thorax, right? So, but immune cells are moving in and out. Every time it moves in and out, it's going to accumulate some dose. So we need to model this. This is the problem we try to solve. So, and different rates, and lymphatic system goes slower than the blood circulation, and different immune cells get killed for different amounts of radiation. So I'm going to go back. I'm going to show you one more thing. I'll close this. Things on here. I'll show you the other one too. Then it's easy. So here we go. So there are two circulations going on here. This is the original one I showed you, but look at this. This is the lymphatics. This is going very, very slowly. It's about 1 day to rotate through the whole body, the lymphatic system. So you need to think about those different motions, different rates, and then also the osmosis between the two that basically connect the full system. Go back in here. Okay. Okay, so we created a predictive model, do all that. I'll show you some slides on that. And we proposed an experiment in NIH, and we got funding, R01 funding. We ran a clinical trial at the Cancer Center here at UVA. Not many patients though. It's 25 in each arm, 50 patients total. It's a phase 2 randomized clinical trial. So it's a medical physicist who is the PI, which is really important to realize that most of the clinical trials are run by MDs, not PhDs. So we, both arms, all the patients got the same type of criteria, standard protocol criteria. In addition to that, we spare the immune system using this predictive model for half the patients. So these are not relevant for us. So here's a cut on the actual cut of the tumor. That, for example, you have the heart, thoracic spine, and the lymph nodes that are highly immune rich. So here's a comparison of the two isodose distributions. This is left in the status quo, and the right for the same patient, sparing these organs at risk. Same thing here. This is the status quo plan and optimized plan. So you can see for the clinical trial patients, the lower doses for the integral dose and the volume receiving 5 gray was quite low compared to standard arm. Here are some results. So this is, we measured the immune suppression at 3 time points, end of treatment, 4 weeks after treatment, and 6 months after treatment. This is the pre-treatment value. These are normalized the pre-treatment value. And the red is the standard optimized arm, and the black is the standard arm. So you can see statistically significant, highly significant improvement in the optimized arm. So this is the first time to show, anybody has shown in a clinical trial setting that you can proactively reduce the immune suppression from treatment planning using this kind of modeling. So not only that, we saw some huge variations in immune increase. So that is important. Remember, I told you about the modulation of the immune system. That means increasing the immune good T cells that we want to use. So we saw that on the optimized arm, a factor of 2 higher immune modulation from this technique. So, and we saw the central tumors that are closer to the heart and the blood vessels are the ones that are benefit the most compared to standard arm. So right now our patients are getting this. Instead, across the world, since it's just a model, we don't need any extra hardware. Everybody could do this, right? That will make our patients live longer and immune system will be spared. So same thing with the other cell types across the board. And we also saw that overall survival benefits. So you can optimize I don't know, I don't expect you to know Kaplan-Meier curve. So in biology or in any medicine, we look at survival of patients. They're called Kaplan-Meier curve. It's basically nothing much except the x-axis is the number of months that a patient lives, and then this is the surviving fraction for those months. So you can see the red curve here is living longer. And if you look at the treatment-naive patients, it's even more pronounced. So you can see there's a nice tail here compared to these standard arm patients that are dying off faster. So you can do a lot with respect to radiation therapy if you want to spare the immune system. So we also identified that the lymph node getting 5 gray volume actually is one of the key reasons why these patients are living longer, see, in both survival as well as event-free survival. So that's the disease-free survival. So our model briefly, we have blood circulation in the original model. We have rates taken from published work, and the blood is moving and accumulating dose during the treatment. So these are all made out of DICOM data. So every patient's treatment plan could be exported from the treatment planning system into this algorithm, and it will automatically run and give you a prediction for a given patient. So the lymphatic model is actually now we are submitting it back with the reviewer comments address. So is a much powerful model, and we saw a lot of new things from this model that we cannot never get it from the patient blood data. So so briefly about our model. So we have 2 systems, blood components and lymphatic components, and the osmosis between the two, and all of the organs in thorax are included in this model. And we wrote a bunch of differential equations and tried to solve it. So this is not AI. So we are proposing a new experiment to do the same thing with AI, but because we did not use AI, we could actually use this as a lever arm to change things. Because if you do it just with AI, it's like a black box. It doesn't tell you what is inside that you have control over, right? But if you build a model like this and add AI to it, it'll make the model better, but at the same time, you can use these lever arms to get better plans, better predictions, and also make the patients live longer at the end of the day. So I'm happy to answer any questions you guys have in terms of the model. So we basically only had 4 variables, A1, A2, B1, B2, that we optimized from the blood data for pre-treatment and post-treatment blood data of the lymphocyte count, that we optimized and found these values and created the model, and now we can predict for any patient for the lung cancer. This was done for early stage lung cancer for 5 fraction SBRT, but it's a very generalized model. That model could be now applied for anywhere else in the body. Right now we have a model for advanced stage lung cancer as well as pancreatic cancer, and I'm trying to add it to the cervical cancer population at UVA. So to see whether this would work for all the other body sites, the treatment sites we have in the cell kit. So you can see here I have a surviving fraction optimization using the linear quadratic model that a lot of people use with alpha beta taken from, again, measured parameters. So we get the time dependent. So this is important. So these are physical systems, right? When you think about modeling, you can think of it as thermodynamics. For example, you have rate equation. If you are looking at the fractional flow rate going from one organ to the other, and fractional flow rate times the absolute number of lymphocytes or immune cells in an organ gives you the actual flow rate. So if let's, for example, imagine that the spleen got hit by radiation a lot, so that means the number of lymphocytes or immune cells in the spleen is going to be lower. So therefore, its actual rate is going to be lower. So that means it's not going to give out more immune cells going out of that organ to the bloodstream. So after the radiation is done, it basically tries to come back to the equilibrium point. So therefore, the immune cell drop and going back up is going to be different from patient to patient, depending on what organ got hit more versus less and how long. So these are kind of the predictive results for our retrospective data set. This is what we use to model our data. And these are some of the results. I will skip this for right now. And agreement between a clinical trial, independent data set is the clinical trial. We applied the model, so you can see here. So again, the same time points in the treatment, 4 weeks and 6 months. So you can see the standard arm data agrees quite nicely, but as I said before, some of the patients end up getting immune increase that is still not modeled, which is actually a really important part, because if we are after the immune modulation term, we need to make this model with that component too, so we can look inside the body, so exactly what's happening with radiation treatment. So some of the results, so you can see again, we have a nice temporal agreement for the standard arm patients, which are done what we use to model, but not for the optimized arm. There are new biologies happening, basically immune modulation, that we need to add in the future. You can see here the blood dose histogram. This is actually the dose accumulated by all the blood particles for a given patient. This is the dose axis, and this is the percentage of the blood cells. And you can see if you compare these two patients, this one got hit less. This is actually in the optimized arm, and it spared the immune system. So, so I'm going to skip this. These are different things that we looked at to see the residual differences. They are nicely independent of all of the variables, as you can see in the p greater than 0.05 range. And survival, we can predict for survival. So if we found out that nadir ALC, that's the dip of the ALC value, is highly correlated with the survival. So even before the patient gets the first treatment, when the patient gets their CT scan, we can do the plan and say where this patient, if they go with this treatment, going to end up. That is the beauty of modeling. You don't need to run a clinical trial. If you have a really powerful model, you can predict for the patient's future, and depending on what the prediction is, you can direct that patient immunotherapy or some other treatments. So that's where I think the field is going with the AI dependent modeling in the future. In the next decade we'll see more and more of this, and it will save us more money and time because we don't have to run actual clinical trials. So some of the other things are these. I promise you this is kind of my last slide because I want to keep some time for you to ask questions. So this is kind of I also want to say something about these models allow us to see into the patient. For example, so we take a scan image, right? CT scan or MRI or PET. It tells you what's inside the patient, what organ is giving trouble or whatever. Like that, if you look at this thing carefully, we have modeled the immune cell changes in each organ. So lymph nodes, as you can see, has the biggest hit. And then this red one is the blood, spleen is the blue. So you can clearly see, you can only get this kind of data from a model. right? So the patient, even before it gets treated, the first fraction, we can have this ready for the physician to see and make a decision on the path forward for that patient. So that is the beauty of modeling, and with or without AI. And I believe combining AI with the standard modeling would give you the best results, because we have a handle to go back and fix the things that we've been doing wrong all along. So I will skip this, and these are just how good the model is. So briefly about how to become a medical physicist. So if you are interested in actually in the United States, so there are multiple different pathways. Professional degree, you can get a PhD in a master's or a PhD from a university and go to clinical residency and do the board certification, ABR, American Board of Radiology. Then you can practice as a clinical medical physicist. There are also non-clinical careers. You can go to industry, you can go work for Siemens or Varian, so you don't need a board certificate. You can stop right here. So most of them are in therapy, and I kind of went through these ones with you. So there's also alternative pathway that basically, if you already have PhD in a different field, not medical physics, you can work with a radiation oncology department, and then get back in the residency and get the campus accredited medical physics residency and go from there. I'd like to thank the patients and families and my collaborators and funding sources, and most importantly, the students who worked on this project. And some of them are here. Thank you. I think I stopped enough time for you guys to ask questions.
Thank you, Professor Wijesooriya, for that insightful presentation. So now we will move on to the Q&A session. I think we had one question in the chat. So is this question is from Vinod De Silva. Is this technology applicable to all tumor types, including solid and also the hematological malignancies?
Yes, it is, but we have only tested so far for a handful of sites. It should work for hematological also, because it's basically immune cells are in the blood.
So online participants, if you have any questions, you can unmute yourselves and post your questions. So I have a couple of questions. So when you did these experiments, did you take into account the level of tumor or the cancer level of the patient, and also what did the amount of radiation correlated with the immune responses afterwards?
Yeah, so that's a really good question. So amount of radiation is really important. So it's actually modeled because individual patients' plans were imported into the predictive model. So individual plans have the CT scans, the structure sets for organs at risk, as well as the dose maps for every one of the treatment fields or arcs. So that was taken into account. So it's a patient-specific prediction. About the other things, like the stage of the tumor, things like that. So right now, the stage of the tumor is taken by the PTV volume, or the tumor volume, because it's higher the stage, larger the tumor volume, or the nodal involvement. So those are all contoured out. But to be specific, current model does not have, for example. So let's say we use 6 liters of blood, but not every patient has 6 liters of blood in our body, right? So you can make it better to be patient specific. Improvements are not in the higher, they are higher order corrections, smaller bags.
So my other question is, so I'm a cell biologist by practice, so I'm more biased towards that. So you said it's not easy, it's not possible or feasible to target just the tumor cells. When you apply radiation, it can attack other cells too. So is it possible to, or is it done already, to like maybe genetically manipulate those tumor cells so that they only attack those cells, or is it an ongoing research on that area?
Yeah, see, that's the difficult with radiation because radiation kills cells. So if we were to modify the tumor, right now we can increase the therapeutic ratio. You can increase the therapeutic ratio for the same plant so that it will be highly radiation sensitive. You can give so hypoxic tumors are not radiation, so you can give oxygenation, or you can use nanoparticles to basically sensitize the tumor. So that kind of things are done.
So we have a question from a student, I think. What are the global opportunities on medical physics as a career?
Global. So what I spoke to you about is only in the United States. So I believe, of course, different countries, for example, Australia, I know, and Europe, they do have a medical physics, and it is actually a career path more than just doing the clinical part. So you have research, and you can have balance. As I said before, so for me, I have clinical research and education, 3 components. So it's hard for me to say how it will be globally, but I know only a handful of countries how it's done. But there's a real need in, like, I work with the Hyper Africa group every weekend. So I know that they have a deficit of tools and education for some countries in medical physics.
We have another question. We are getting questions now from Mahesh Jayakodi. How do you scale the model to be accurate in radiotherapy while balancing with computational power?
So yeah, I didn't go too much into detail. Actually, one of our published papers has those numbers. So it is really, really important to have a prediction fast, because you can interface these predictive models with the treatment planning system. So in real time, when you have a plan, could use this information to guide their plan so that it has to be fast. So it is quite fast the way it is created right now. But that's a very good question, because you can have all these minor details and really slow you down. So it becomes not very practical to use in the clinic, because clinic is a fast moving place.
We have another question. Out of traditional statistical models and AI-based models, how do you decide which approach is more appropriate for a given clinical problem?
Yeah, that's a good question. Actually, I have 2 types. I didn't have time to go into that more detail. For example, if you take early detection, let's say somebody want to make a model with early detection of lung cancer or pancreatic cancer. So in that case, you would basically use the data and come up with some predictive models. You don't need statistical models. You can simply do AI, because the model can be a black box. There's nothing you need to control, right? You are looking for a prediction that will tell you earliest time points you can detect the tumor. So there are different clinical scenarios that you could go with just AI.
We have, I think, another question. This might be of interest for most of the undergraduates here. The question is what are the typical prerequisites for to apply for a PhD in medical physics? Is a bachelor's in physics a must?
Yeah, so bachelor's in physics is what people here use. So they have bachelor's in physics or engineering. It doesn't even have to be physics. So some of my students they had engineering background. So bachelor, so physics related field. So you can have a physics related field and then you can apply for a PhD in medical science. And if you don't have that, you can still have a chance of going the certificate program. Let's say you have already done your PhD in, let's say, nuclear engineering, right? So you can apply for the master's program and do that. So there are, I believe, the fields get stronger when you have people coming from different backgrounds, because they look at the problems in a very different way. You look, from your training.
Thank you. So another question is, how do you validate these predictive models across different patient populations or institutions?
Yeah, that's a good question too. So you have to validate them. It can be so my next step is actually to run this clinical trial in a multi-institutional setting, because institutions run different image generation processes, and their contouring can be very different from what we do. And so we have to validate and find the uncertainties all of these bring in. And even if you go to different countries, let's say I want to run this trial in Sri Lanka, right? So there are different, and my clinical trial had only 1 or 2 Asians. So the populations are very, very different. So I would not say this model is, even though it has all the ingredients, it might have to be adjusted for Sri Lanka. So it's really important that the next generation of models are validated across different ethnic groups, because that is very easy to do, because you don't need anything extra in hardware, because these are all software modeling, right? So you just need to run a clinical trial with the software that anybody could do.
The next question is, what are the biggest barriers to translating these predictive tools to routine patient care?
Yeah, biggest barriers is it takes time. So you have to get FDA approval. If you have a product, you have to go through a process so that you can legally, safely, and however better it is. You see, it doesn't matter that you can show that it is better, like what we have shown here. You still have to go through the pathway of FDA approval and things, even for software products. So it takes time. So it takes time to go from the model to the bedside. I only talked to you about the bedside to the model. Now to go back to the bedside. So it takes time. Yeah. But it is good to have those barriers, because then you acquire more data, you look at the thing more carefully, and only use the positive thing.
Yes. I think this is the final question for today. Does hypoxia or metabolic environment influence immune suppression differently across sites?
So hypoxia is shown to affect the tumor kill. So oxygenation for the immune cells, it could have an effect, but nobody has actually modeled that right now. But on the other hand, immune cells go through lungs. It gets oxygen naturally, right? So unlike the tumor that is restrained from the blood vessels getting the blood to the center of the tumor, immune cells circulate. So it's a much less of an effect.
Yeah, and the environment across sites. That was the second part of it.
Pardon me?
The second part of the question was the environment influence across sites.
Across sites. So, environment, sites means the organs, or is it organs I'm assuming? Different organs?
I think so.
We have added that part actually in our model. We have different organs. We know the immune densities and the flow rates and all that stuff. But if you are referring to sites in different clinical places.
No, I think it's the organs, metabolic
Yeah,
environment.
Organs. Yeah. So it is basically modeled with published data.
I think that's all for the questions
On
we
time.
have, I think.
All right.
So
all right. Thank you very much for the opportunity.
hang on a minute. So with that, I would like to invite Professor Wijesooriya to thank our speaker for today.
Thank you very much. Good morning, good evening, everyone. So on behalf of the Faculty of Science, University of Colombo, I would like to express my sincere thanks to Professor Krishni Wijesooriya for her very interesting and informative talk, which focus on the development of clinical trial. So we truly appreciate the way you explain your ideas and experience in a clear and simple manner. So your presentation is highly valuable, I think, especially for our students and our young researchers. So actually, the Professor Krishni is one of our collaborators. He is helping two students at the Department of Nuclear Science to MPhil projects. So thank you for taking your time to share your valuable knowledge and experience with us today. So I would also like to thank the organizers, our Faculty Alumni Association, for arranging this kind of session, and all the participants for joining. So thank you very much for the opportunity. Thanks.
Thank you. It's a pleasure. Have a great night.
Okay, see you soon next week, I think.
Darshan, you are muted here.
Thank you, Professor Jayasingham, and thank you again for our speaker. And see you all in our next talk.